Hello, universe. Today we are going to be discussing the change of variables theorem. Given an open set omega of Rn and a change of variables g from omega to Rn, which is a C1 diffeomorphism. So what this means is that the mapping G should be injective, and at every point its differential matrix, which is in coordinates the Jacobian matrix of its partial derivatives, needs to be invertible. Okay, so essentially the differential map should be invertible at every point, and the C1 condition is requiring that the partial derivatives of G are all continuous. Okay. Now, given a Lebesgue measurable function f on the image of G, the pullback of the function f by G is again Lebesgue measurable on omega. Okay? And the second part of the theorem states that if we further assume our function is positive or integrable, then the integral of this function over the image of omega is equal to the integral over omega of the pullback of the function f by the map G, scaled by the magnitude of the determinant of the Jacobian matrix of our change of variables function G. Okay? And this integration is done with respect to the Lebesgue measure on Rn. Okay? So let's quickly comment about Lebesgue measurable functions. Recall that a function is Lebesgue measurable if the inverse image of measurable sets remain measurable. Okay? And since G is a C1 diffeomorphism, it will have an inverse, which is defined on its image, and that inverse function will also be a C1 diffeomorphism. So it follows that if f satisfies this condition of that its inverse image of sets preserves measurability, then that will definitely hold for the pullback of f by G, right? Because G itself is invertible, so G is going to be a measurable map, right? And so our goal is to prove this theorem. Now, what we need to understand is how the theorem works geometrically. What is this theorem saying, and why should it be true? So what I'm going to give you today is a proof sketch of how one might prove the theorem using ideas rather than actually just doing a rigorous step-by-step proof, because you can certainly find one in Folland if you reference this textbook here. Now, the proof structure that I'm going to offer you for this theorem is actually going to be slightly different from the approach of Folland. Okay? Let's take a look at these pictures that I've drawn. So here I've drawn omega as a subset of Rn, and I've basically partitioned omega via a grid into cubes, okay? And these cubes are supposed to have relatively small volume, okay? So this grid is essentially going to get finer and finer as I send the radius of these cubes to 0, okay? And now I focus in on a single cube, and I look at the image of this cube under the map G, okay? So the image of this cube under the map G, it's going to be some distorted object, but locally it should look something like a parallelepiped. And that parallelepiped is essentially the image of the cube under the differential map, namely the linear map, which is the differential of G at the center of the cube P, okay? So the idea is that since this differential, in coordinates, it's the Jacobian matrix of partial derivatives. All of those partial derivatives we've assumed are continuous, and so therefore, in this small cube, the differential map is actually not going to change very much, okay? So if I vary P here, then this differential map, it's going to be a linear map which sends this cube to a parallelepiped. The parallelepiped will be framed by vectors that are the column vectors of the Jacobian matrix, okay? And the volume of this parallelepiped will exactly be the volume of the original cube which you can think of as dx, some small volume, scaled by the determinant of the Jacobian, okay? And that's actually the geometric interpretation of the algebra behind the determinant is that the determinant of a matrix geometrically is the signed volume of the parallelepiped spanned by the column vectors of that matrix, okay? So the determinant is truly encoding the local volume distortion of the change of variables map G, okay? But this isn't fully rigorous yet because in this case we can understand the volume distortion induced by the differential, but the mapping G itself is not a linear map. So G is not a linear map. It's not actually mapping this cube to a parallelepiped, but what we want to show is that actually if this cube is small enough, then the image under G is something that can be squeezed between two parallelepipeds that are very, very close together, okay? Okay, so let's zoom into our cube here. This is a cube in omega, okay? And it's centered at the point P, and I want its side length to be small. So let's just say its side length is epsilon, where epsilon is a small number, okay? And I've drawn here a line through this cube, and this line has direction vector V. Now, I want to think about this cube in two different ways. The first way is I want to identify this cube with actually a cube in the tangent space. So here's the tangent space, TP of omega, which is just identified with Rn, okay? And the tangent space, to Rn is itself. So I'm really just going to kind of include the tangent space into Rn and kind of view these as the same sets here. And so that I have the same line. But in particular, I know how this tangent space gets mapped to Rn via the differential, okay? So the tangent space is going to get mapped. Let's put the tangent space over here. The tangent space is going to get mapped via the differential or the Jacobian matrix, okay? And the vector v here, in particular, the vector v is going to get mapped to the vector which is the image of v under the Jacobian, okay? So that's this vector that I've drawn here. Now, the parallelepiped itself, of course, the parallelepiped is framed by the column vectors of the Jacobian, and the volume of this parallelepiped is essentially the volume of the cube scaled by the determinant of this linear transformation up to a plus or minus sign, so the magnitude of the determinant. And so now I want to kind of view this parallelepiped as an approximation for the true image of this cube under the map G, okay? So what happens when I actually use the mapping G instead of just the differential? So when I actually use the mapping G, let's focus in on this line here with direction vector V. This line is going to get sent via G to a curve in Rn, and that curve is going to have a tangent vector, which is precisely this tangent vector, which is the image of V under the Jacobian. That'll be the tangent vector to the curve at G of P, okay? So, but now the curve might have slightly different behavior. It's not necessarily going to be a line, okay? So it's going to have some sort of behavior like this, where now it's no longer necessarily a line, okay? However, let's focus in on this curve, okay? So if I focus in on this curve here, okay, then I know that at every point on the curve, so here's maybe G of P here, and I know that the tangent vector at G of P to this curve is just the image under the Jacobian at P of the vector V. And at a different point on the curve, let's say G of Q, where Q is a different point on the line here, okay, and this identification is unique because G is a diffeomorphism, so G restricted to this line is a diffeomorphism. The tangent vector at G of Q is no longer the image of V under this differential map. It's the differential map at the point Q of G acting on the vector V. Okay, so this might be a slightly different vector. Okay, it might have a slightly different direction. However, when I scale this cube to be within epsilon of the side length of this cube to be with an epsilon, then I know that since the partial derivatives of g are continuous and the cube is compact, then the idea is that that I can ensure that the partial derivatives of g, which make up the elements of my Jacobian matrix, are going to change at most by a constant multiple of epsilon. Okay, so the idea is that this sphere here that I've drawn here, any vector inside this sphere is basically an admissible tangent vector to the image of the curve under G. Okay, so this sphere that I've drawn here is of radius. So the sphere has radius given by some constant multiple of epsilon. Okay, and that constant is essentially a constant which ensures that, you know, as I move within my cube, as I move around in my cube, the elements of my matrix of the Jacobian are going to change at most by a constant multiple of epsilon. Okay? Now, what does that mean? That means that all of these tangent vectors to the curve here, all of the tangent vectors to the curve must belong to some vector in this sphere here. Okay? So what that means is that the difference between this curve and the line, okay, the line which is the image under the differential map, the distance between these two, okay, is at first it's 0, okay, and it is growing at a rate which is a constant multiple of epsilon over a distance which is also a multiple of epsilon, okay? So this distance here is a linear multiple of epsilon, along which this difference between the maximum difference between the true image of this line and the image of the line under the differential, okay, that distance is growing at a rate of epsilon, okay, because the sphere has radius constant times epsilon, but moreover, it's growing at a rate of epsilon over a distance which is of order epsilon. So in particular, the distance, the final distance between the endpoint of this curve and the endpoint of the line on the edge of this parallelogram, this distance is of order epsilon squared, okay? That's a key realization, is that in fact, we're gonna be able to force that that if I choose epsilon small enough, the distance between this curve here and the line, which is the image of the differential, is going to be in order of epsilon squared. So what that means is that if I just look at where G sends the boundary of this cube, G is going to send the boundary of this cube into some region, but that region is an epsilon squared neighborhood of my parallelepiped, okay? So the true boundary of the cube gets mapped to a region which is within an epsilon squared neighborhood of the boundary of this parallelepiped, okay? So in particular, as I scale epsilon down, the accuracy of my approximation is growing. Even though the length scale is shrinking at a rate of epsilon, the accuracy of this parallelepiped in determining the local volume distortion of G is actually growing. And so the image of this cube under G is getting squeezed between two parallelepipeds, which are a distance epsilon squared apart. Okay, and so in fact, the volume of this image of this cube is well approximated in the limit, as you send epsilon to 0, is well approximated by the volume of this parallelepiped. Okay, so this is a complicated logic. Let me just explain it one more time. Okay, the logic is the following. We look at the image of the cube under the differential map. That's a parallelepiped, okay? Now, every line here passing through the boundary of the cube is going to get mapped via the differential to a line which goes through this parallelepiped, okay? And then we're going to have a sphere centered at this vector here. A sphere centered at this vector. This sphere is going to have a radius which is a constant multiple of epsilon. and it's going to represent the allowable, anything inside of the sphere is an allowed tangent vector to the true image of this line under the mapping G, okay? And so in particular, the distance between the true image of the line and the image of the line under the differential, that their difference is growing at a rate of epsilon, at most constant multiple of epsilon, okay? And it is undergoing that growth over a distance scale, which is also a constant multiple of epsilon. So in particular, this distance can only change by a factor of epsilon squared. So that allows us to squeeze the image of the cube under G into two parallelepipeds, which are within epsilon squared distance of the image of the cube under the differential map. Okay, so that error is going to decay faster than the length scale, which we send epsilon to 0, which means that this approximation will become more and more accurate as we shrink our cube size down and do, a Lebesgue covering of a measurable set by a smaller and smaller size cubes, more and more cubes, but smaller and smaller in size. We can approximate any set by this collection of finite cubes, and their radius is shrinking. However, the accuracy of this approximation here of the local volume distortion is actually getting more and more accurate, despite the fact that the radius of the cube is shrinking, okay?